Okay, here's part 2 of this Edexcel Linear 2024 paper for A-level students. So it's called Advanced Physics 2, which is equivalent to or closest to the IAL Edexcel Unit 5 with the additional questions on Unit 2, waves from Year 12, and some questions on materials. So I've already gone through the multiple choice and up to question 14 in the first part, which you can find in the same playlist. So I'm going to go straight into question 15. Okay, so if you found the first video useful, give it a like, share it with your friends, and let them know that I'm starting to do linear papers alongside the more common international A-level Edexcel papers that I've been doing since last year. Okay, we've gone well over 1,000 subscribers in this exam season, and we're close to monetizing the channel, so your support would be greatly appreciated. We nearly hit the criteria to be able to become a partner with YouTube. Okay, all right, so straight into it. A student wound a piece. Let's just make sure the Apple Pencil's working. A student wound a piece of string around the head of an electric toothbrush. Okay, it's not very clear in the picture. The student attached a small mass to the other end of the string as shown in the photograph. Okay, so presumably this is the small mass. There it is. And this is the head of the toothbrush. Oh, I can see it now. There's the toothbrush. And the string seems to be wound up on the head of the toothbrush. The toothbrush was switched on and the head started to vibrate. Okay. The student rotated the toothbrush slowly to unwind the string. So in other words, to make the string longer. So this would be the length that he was unwinding. At a particular length, large vibrations were observed on the string. So we got resonance. Okay? The string formed a loop. That's the form of resonance for those of you who've done Unit 5, as shown in the photograph below, photograph 2. So this is setting up a stationary wave, yeah, which is from Year 12. It's from the IAL Unit 2 waves topic. Okay, so you can see that it's got one loop, so that's one antinode. Yeah, and therefore it's got two nodes at the fixed points. Okay, so these will be nodes. And if you got two nodes and one antinode, that will be called the fundamental frequency or the first harmonic. Okay, so resonance is a Unit 5 topic. So it does make sense to link Unit 2 and Unit 5. Okay, so this is from the last video. I didn't show you the mark scheme for question 14. So if you looked at question 14 and you thought, where's the mark scheme? It's just the way I had double-sided the PDF. So I couldn't put it there because it's probably got question 15 on the back. Okay, so if you want to have a look at what you did in question 14, I'll let you stop the video and do so. And here's question 15. So we haven't actually got to a question yet. So question 14 is there. We've got the scenario. So it looks like question 15 is talking about how are standing waves set up, because it's talking about waves are produced by the toothbrush oscillating, vibrating, and then reflected at the other end where the mass is, yeah, and then the waves meet and superpose, yeah, and you get constructive interference at the antinode because the wave and the reflected wave are in phase, okay? And then the rest of it will come back to these 2 points. So let's go and read the question and see if we can answer it. It says, explain how vibrations of the toothbrush cause the loop to form. Okay, the loop being the antinode. So wave and reflected wave, as we just saw on the mark scheme, they meet and superpose. So these are technical terms I want you to include when you try to answer this question. And for some of the students who watch my YouTube channel, say I mustn't write in bullet points, I must write in full sentences. Well, no, the person taking the exam has to write in full sentences. I have to give you help in what to include. So I'm giving you the key terms, and you've got to practice explaining, yeah? So the key word here is explain how, yeah? So you've got to explain it, and I want you to practice doing that, okay? So constructive interference occurs when they're in phase. Destructive interference occurs when the wave and the reflection are anti-phase. Okay, out of phase is better to say anti-phase. Okay, so I should have put this as an anti-phase, exactly the opposite. So a peak meets a trough. This is more accurate than saying out of phase. And an antinode in the center is where you get the maximum amplitude. So these are all things that you need to be aware of. Nodes at the ends, where you have low amplitude or zero amplitude. Okay, obviously there must be a little bit of vibration, otherwise it wouldn't start. And then at certain frequencies, standing waves are formed or created, yeah, because it's basically a form of excitation or resonance. It's when the vibrating frequency of the toothbrush matches the natural frequency. It's another key word here, the natural frequency of the string. So this is linked to this point here, okay? So whenever something is being forced to vibrate, if the forcing frequency matches the natural frequency, now we're talking about Unit 5 or Year 13 content of linear, then when the forcing frequency, I've written it here, matches the natural frequency of the length of string, you're going to get large amplitudes, okay? So that leads to the large amplitudes. And that's a form of what we call resonance. Everything has a natural frequency, and if you hit it, if you hit that natural frequency, it will cause the kind of patterns that you see on vibrating strings. Okay, so go back to the mark scheme, and we went through the first 3 bullet points, and the next one says the string vibrates at the center with maximum amplitude. That's the antinode, yeah? So the antinode is formed in the center, okay? You can also mention the reverse, where there's a 0 or minimum amplitude. I think minimum is probably better. Then you have nodes forming, okay, the fixed points. And this is what creates a standing or stationary wave, okay? So it's 5 marks, this question. There is an alternative method here that they're allowing. So let's have a look at it for the sake of completion. The toothbrush causes the string to vibrate at its natural frequency. That's what I was explaining to you. There is a maximum efficient transfer of energy from the toothbrush to the string. Yes? So that, for example, if you're pushing a child on a swing, you get the maximum transfer of energy to the child on a swing if you keep pushing it when the child is reaching the end of a swing. Okay, and that's what you do when you push someone on a spring. And this is called resonance. Yes, so when you're matching the pushing or the periodic oscillations or the periodic pushes, then with the natural frequency of the object, in this case a string, resonance occurs. And resonance basically means large amplitudes, which is in the next bullet point. So the vibrations, the string vibrates at the center with maximum amplitude, yeah, and an antinode in the center. And this is what creates a stationary wave or a standing wave. So you see both of these, I included both of these in my notes for you. So it just depends. This is more the year 13 version, yeah, and the yellow bit is more the year 12 way of doing it with stationary waves. Okay, superposition. Okay, so we've done another question, part A. Part B then says the student continued to unwind the string and the loop disappeared. Okay, because the length changed, the natural frequency changed, yeah, and it no longer matched the frequency of the toothbrush head. When the length of the unwound string was twice that shown in photograph 2, you got 2 loops forming. So 2 loops were seen. 3 loops were then seen when the unwound length was 3 times that shown in photograph 2, and so on. So 2 loops would look like that. 2 antinodes. Of course, they would also do the reverse of that vibration because they're constantly moving up and down. And 3 loops frozen would look like that. Okay, so that would be the second harmonic, 2 loops. The third harmonic, 3 loops. Okay, they want you to determine the frequency of vibration of the toothbrush head. Okay, so the unwound length of string with 4 loops, which we haven't talked about so far, so there's 4 loops. 1, 2, 3, 4. 2 on top, 2 underneath, there's 4 loops. So with 4 loops, it's 0.69 meters. Now 4 loops is exactly 2 wavelengths. So you now know the wavelength of produced is 0.345 meters. Okay, just by knowing that 4 loops is 2 wavelengths, and they're giving you the length of the string. The mass on the string was 0.01 kilograms to 2 significant figures, and therefore we know the tension because the mass is producing tension. And the other thing you need to know for the year 12 content is the mass per unit length of the string. Mu, this letter mu, is needed as kilograms per meter. Okay, so it's basically the mass over the whole length. Okay, so if you weigh the object, you can then divide it by the length and you'll get the mass per unit length. So once we got the weight, we know the tension. By using G, you can get it in newtons. Okay, then we have to use the wave equation for a string. And you can see that the velocity is going to be 10.4 meters per second. I think if you just divide the tension by the mu, you can actually work out the velocity. But we want to work out the frequency, yeah? So remember, they want us to work out the frequency. So to do that, we can change the equation from this, V, by using F lambda. We can change V to F lambda. And then we know that lambda is 2, is the lambda, we know lambda, yeah? So we've put lambda into here, and we make frequency the subject of the equation. So F lambda would be V, divide both sides by lambda, you get 1 over lambda. We know lambda, it's 1 over 3.345. We know the tension, and we know mu, so all you've got to do is put the numbers in, and you get 30 hertz to 2 significant figures. So that is the frequency of the toothbrush head. And that's 10 marks. Okay. there's the rest of the question that we just did. That's 15b. Question 16 looks like it's a simple harmonic motion because you got frequency and you got the equation for the period of a spring mass system. Okay, so we're using a spring mass system and doing some calculations. Looks like you got an astronaut. Yeah. Okay, and then 16b, we are using amplitude, angular velocity, maximum acceleration. Looks like simple harmonic motion here. So this will be about simple harmonic motion. And then you do the velocity. Looks like it's maximum velocity. We'll have a look. Okay, so that's what we're doing next. I actually did this paper a while ago, and I haven't looked at it for a while because I don't have that many international Edexcel linear students. So I just gave the copy to them on PDF because I didn't have time to record it, and I just managed to get a chance to do it tonight. So I thought I might as well add it to the videos. Okay, question 16. On the International Space Station, ISS, astronauts measure their mass once a month. Okay, using a body mass measurement device, because obviously they can't just stand on scales because there's no gravity pulling them down as such. Okay, the BMMD is constructed from a large spring attached to the floor of the ISS with a platform and handles attached to the spring. So it looks like he's holding onto the handles here. Yeah. And he's pushing on the platform. So the spring is compressed and the astronaut puts his body onto the platform and holds the handles as shown. Okay? So inside the cover there is a spring. And the spring will have a certain stiffness. The spring is released and the astronaut and the platform oscillate with simple harmonic motion. So simple harmonic motion is year 13 content, so I put the IAL unit number, IAL unit 5. So an astronaut used this device and the frequency of oscillation was 0.34 Hertz. Well, we know, then we know the period. We can calculate it straight away, which is kind of what I tend to do before they ask me what to do. They want us to determine the mass of the astronaut, m. Okay? The mass of the platform is already 5.7 kilograms, so that's going to be part of the mass that's oscillating, and the spring constant is given at 350 newtons per meter, so we know K and we know the mass of the platform. Okay? Now this mass in this equation, which is the spring mass system, will be the total mass. Okay? So they want us to work out the mass of the astronaut, so all we got to do is work out the total mass by getting rid of the square brackets, and we can make the mass, I think it says MT for mass total, the subject of the equation, if you can see what I've done. We know K, we know the period from here, so the period can just be put into this equation, and obviously we know 4 pi squared, so it's just putting numbers in. So then we get the total mass is 76.6. Yeah, so that's the astronaut and the platform together. You take away the 5.7, which is the mass of the platform, and you get the astronaut must be 70.9 kilograms. Okay, so I should really put that in there. Yeah, and do we want 2 or 3 significant figures? So you can either do 2 or 3. So this is 3, because the data provided is, I would just do it to 2. Okay, so don't even know you can know your mass that accurately. fluctuates each day. Okay, part B. The distance between the upper and lower points of the first oscillation is 0.29 meters. Okay? From the upper to the lower points, that means it's twice the amplitude. Okay? Because the amplitude is from the upper point to the equilibrium position, whereas they've gone from the upper point to the lower point, which is amplitude in the positive direction, amplitude in the negative direction. So we know the amplitude is half of that, so we now know the amplitude. Okay, because we're going to use some simple harmonic motion equations. Calculate the magnitude of the maximum acceleration of the astronaut. Okay, so the maximum acceleration is given by minus omega squared x, the defining equation for simple harmonic motion. Okay, now the A max will be when the displacement, is equal to the amplitude. So all you've got to do is to work out the answers. We know the frequency from before, so we can work out omega is 2 pi f, yeah, and f was 0.34, and we know the amplitude, we just worked it out, put the numbers in, yeah. So omega from here shows you what it is. So you put them in and you get the answer 0.66 meters per second squared magnitude. That's the maximum acceleration. Obviously the maximum acceleration occurs when you are most displaced from the equilibrium position. Then it says calculate the speed of the astronaut 3.5 seconds after the start of the oscillation. Okay, so speed is a scalar, so we just need the size of the speed. So v equals a omega sine omega t with a minus there. We can ignore the negative because they're asking for a speed, not a velocity. Okay, so we know a and omega. I think a is 0.145, wasn't it? Yeah, a was 0.145 and omega is 2.14. So you just multiply those two. There should be a minus sign, mathematically speaking. And then you put sine omega t, where t is 3.5. We know omega again. And you need to make sure your calculator has radians. You need to do some radians. Okay? And once you do that, you get v equals 0.29 meters per second. The reason it needs to be in radians is because the values in front of the sign are not in degrees. Okay? And again, this is not 3 significant figures. This is actually 2 significant figures. So that's 2 significant figures. And I think that's what you should put in your answer. Okay? So another 10 marks done. Question 17 is about a hot air balloon, which has got a fabric envelope. It's got heaters and a basket as shown. Okay? Obviously the heaters are there to heat the air in the balloon. Yes? So this is called an envelope, the balloon. So it says here, I've written that as unit 5. Let's see if there's any upthrust. If there's upthrust, that's from unit 1 as well. Okay? When the balloon is set up, the envelope is partially filled with air at 20 degrees centigrade. So this is unit 5 because it's thermodynamics. Temperature is 293. The air is then heated to 120 degrees centigrade and expands to fill the envelope, which becomes less dense. Okay? So the second temperature they heat it up to is 393. Okay, so temperature change of 100. The air pressure inside the envelope is always equal to the air pressure outside the envelope. Yeah? Because the envelope is open at the bottom. So if the pressure was different, if the pressure inside was higher, air would move out. And if the pressure inside was lower, the opposite would happen. So the air will move to equalize the pressure. So that's true. Okay, the balloon takes off when the upthrust is more than the total weight of the balloon. In other words, when you've heated it up to the density becoming lower, so it will rise. The air in the envelope. Yeah, weight of the balloon, the air in the envelope, and the passengers. Okay, so that's all the weight. The weight of the balloon, the air in the balloon, and the passengers, as well as the basket, I suppose. Okay, so in other words, if upthrust is greater than W, you'll get takeoff. That's the condition. So we got to deduce, that's our job, is to deduce whether the balloon can take off. That's our job. Okay, haven't done that very well. Okay, they're giving us all this data. The volume of the air initially was, it's a final volume, okay? They're given mass of the balloon, mass of the passengers, and the density of air at 20 degrees centigrade. Okay, so that's the density of air at 20 degrees centigrade. So the mass of the air is going to be the volume. So volume 2, what's volume 2? I think that's what they've put, times the density of the air at 120. So we want the second volume, the expanded volume, okay, which we have 2,800, yeah? So the mass of the air must be constant. Is that what we're saying? Yes. So the volume 2 times the density of air at 120 degrees centigrade must equal the volume 1, the initial volume, times the density of the air at 20 degrees centigrade. Okay? I think that's what I'm saying. So bear with me, because I did this solution quite a while ago. So we know that pressure times volume is equal to nKT. Yes, it's a gas law. So P1 and P2 cancelling out. Why is that? Pressure, oh yeah, so pressure is always equal to, because of that. So P1 and P2 are always the same because of what we said over here. Okay? So then you got, I basically put T on the other side of the equation. So you got P1 V1 over T2, T1 equals NK, and that means P2 V2 over T2 will equal it. And for those of you who know this formula of the gas law, you can just do P1 V1 over T1 equals P2 V2 over T2, and since the P's are equal, you can actually get the ratio of the volumes and the ratio of the temperatures in a useful equation, because we want to work out volume 1. We know volume 2, that means the volume at 120 degrees centigrade. So we know volume 2, we know temperature 1, and we know temperature 2. There's temperature 1, there's temperature 2. So the only unknown is V1, so you put V2 in, 2,800, ratio of the temperatures, and you get the initial volume. Okay, so now we can, so this bit here, we put 1/3 color here, this bit here, which I was trying to explain to you, we don't need it until now. So now that we know volume 1 and volume 2, and what are we trying to find out? Whether the balloon can take off. Okay, so we want to know the upthrust of the balloon if it's greater than the weight. Okay, so the mass of air in the balloon, I've said, is equal to the mass of air at 20 degrees centigrade, which is the volume 1 which we just calculated. So we can put this volume 1 into here, and we know the density of air at 20 degrees centigrade. There it is, 1.2 kilograms. So you multiply the volume 1 by the density of air at 20 degrees centigrade, and you know that the mass of air you start with was 2,505 kilograms. So the total mass will be equal to the mass of the air plus the mass of the people plus the mass of the balloon. Okay, so we know the mass of the air, we just calculated it. We know the mass of the balloon, and we know the mass of the people. So the answer is 3,225, accurate value to 4 significant figures. So they haven't actually asked us to do anything, but they wanted us to deduce whether it will take off. Yeah, they have, so 6 marks. And we have to look at the mark scheme to see if I've got everything in there. Okay? I'm just wondering if I have confused anyone with this blue bit. Are you aware of this bit? So is the mass of air constant? Yeah. So volume, if the density will go down, yeah, the volume was higher, the density was lower. So I think that makes sense. The volume at 120 degrees was bigger, 2,800, before it was less. So you've exchanged volume for density. Okay, the expansion causes a loss of density. So I think it's fair to assume that the mass of the air is constant. Okay. All right, so then we go to the next page and we get the total weight, because we know the total mass. So we multiply the total weight mass by 9.81. Okay. W equals mg. So you just multiply by 9.81. You get 31,637 newtons to 5 significant figures. And the upthrust is 33,000 newtons. Okay? How did we get the upthrust? Upthrust is given to us. See, such a long time ago since I did it. So they've given you the upthrust. I was wondering if I'd missed a thing. So the upthrust is given to us. All we had to do was to work out whether the weight is less than 33,000, and it comes to 31,600 to 3 significant figures, and the upthrust was 33,000. So if you want to do it till 32,000, there's still more upthrust than weight, so it will take off. Okay, I think I got through that okay, having done this like I don't remember when, a few weeks ago. Okay, it then says state one assumption of the kinetic theory gases. You can have a look at the mark scheme because there's many accepted answers, yeah, and it's good revision notes. So we'll have a look at that afterwards. Okay, so remind me. And then it's now a derivation. Derive an equation to show that for a temperature T for a gas, the mean kinetic energy is given by the known equation 3/2 kT. Yes, KT, a girl's name. That's how I used to remember it when I did my A-level many years ago. So we know that PV equals NKT. We used that equation before. And we know these equations are given to you. PV equals 1/3 NMC squared, where C squared is the root mean square speed. Okay, or the mean, so I should say the mean square speed. Yes, C with square brackets. It's the mean, that's what square brackets are, square speed. Okay, mean square speed. So you can equate these two equations. That means NKT will be equal to 1/3 NMC squared. Then the n's cancel. KT equals 1/3 MC squared. But we want to have something with 3/2 KT. So if we multiply 3 halves both sides, yeah? So you then get 3 halves kT on the left, and you multiply 3 halves on the right as well. 3 halves times the third becomes a half mc squared, and that is the mean kinetic energy of the molecules. Okay, so we've proven it. Job done. So this will probably be something worth doing before your real exam, because they can always ask this again, and if you've done it once, then you'll be very confident if you get a question like this again. And it's only worth 2 marks, but it's a good thing to have up your sleeve in case they ask it again. Okay, let's go and have a look at the mark scheme and then come back and do that final bit. So here's the first bit. Yeah, they've made a mistake in the mark scheme here. I can't see the mistake, but because I've scribbled over it. Yeah. Oh yeah, they left the T. Yeah, but you can see we made it P1V1 over T1. They left the T in the middle where the NKT was. They forgot to cross it out. Okay, that's all. So this is the first part, and these are the assumptions for the kinetic theory of gases. Yeah. So we're talking about the particles in the kinetic theory of gases, ideal gas, are point particles, and the particles have negligible volume, yeah, compared to the volume of the whole container. In other words, we can assume that their volume can be ignored, and there are negligible forces between the particles, yeah. In other words, we don't think of the attraction between particles over a large distance. So the only time we have forces is when there is a collision. So these are all conditions to have an ideal gas. In other words, under high pressure, real gases do not behave as ideally as under low pressure, because obviously under high pressure, the forces will become significant because there are attractive forces between particles, molecules, and the range of molecular forces is small, yeah, compared to their separation. In other words, we can ignore it, again, unless you have high density, high pressure where they come close, okay? And the duration of collisions is negligible, yeah, so we can ignore it in comparison to time between them, and we can use Newtonian mechanics, okay? And particles move with uniform velocity between collisions, because obviously there's no other forces involved, because we're ignoring the forces, and we can assume for once that the collisions are elastic, yeah, elastic collisions, and the particles move with constant random motion. So any of these points will get you the mark. So you need to know these in your revision. Okay, so I think we got one bit of the question left to do. I think this is the bit that I showed you before, yeah? And we just got one part left. I think we haven't done 17, B3, this bit we haven't done, yeah? So we're using the atomic mass unit to determine the particle's mass, and then using the equation that we just proved, we're using that, looks like, here, to work out the RMS speed, yeah? Not the mean square speed, but the square rooted, the root mean square. So you're going to square root the squared speed. And I think we're ready to have a look at that. So it says, calculate the mean square speed, the root mean square speed of nitrogen molecules at a temperature of 120 degrees centigrade. So first trick is make sure you know you change to Kelvin. You need the mass of a nitrogen molecule is 28 U. U is given on your data sheet as 1.66 some 10 to the minus 27. So you just multiply by 28. You get the mass in power 10 to the minus 26 kilograms. So we know the mass of the molecule to put into here must be in kilograms, yes. And once you do that, the only unknown will then be c squared, because k is given to us in the data sheet. There's k, and you can see that on your data sheet. Okay, everything else, temperature we know in Kelvin, and you put the numbers in, make c squared the subject of the equation, and then you've got to square root it. So this is the c squared value, and you square root that, and you get 590 meters per second. And there is another 3 marks, another 12 marks, question done. Question 17. Okay, question 18. It reads as follows. In 1864, these two guys, Huggins and Miller, used dark lines in the spectrum of the sun to identify elements in the sun's atmosphere. So why are there dark lines? What do we call dark lines? The dark lines are called absorption spectra. The dark lines indicate the frequencies which have been absorbed. So this is spectra you would have met in Unit 2, and you will meet them in Unit 5 because of astrophysics. Okay? So it's Unit 2 and Unit 5 because of energy levels comes from Unit 2. So what's the question actually asking? Yeah, it says explain how gases in the sun's atmosphere cause dark lines in the spectrum. Yeah, and how they correspond to different elements, because every element will have different energy levels. So they have different energies that will cause excitation. Yes, so because excitation means that there is a discrete change in the level that the electron can go to in an atom. So you get this by absorption of photons. Specific photons will correlate with the excitation levels. So only those, for example, it might jump up from this level to this level, and that will correspond to the absorption of a photon of energy of a specific frequency. So this frequency that corresponds to these 3 lines, you could say this is n equals 1 and this is n equals 4 energy level, then that will be absorbed. You can then also get energy going from here to here, and that will be a smaller frequency, but each of these are discrete energy levels or energy transitions. Yes, this one and this one. Okay, 2 different energy transitions which are discrete in their value. So the HF will correspond to the differences in the energy levels, delta E. Okay, each element has unique spectral lines because it has unique energy levels. Okay, so each element will absorb unique, different frequencies. Like a fingerprint, each element has a specific pattern of absorption lines. And absorbed frequencies look dark compared to the rest of the spectrum, which will still be equally bright as before. And the reason they appear dark is because although they are absorbing those frequencies, specific frequencies, they also have to re-emit them, because what goes up also goes back down again and gives off the same frequency. Yes? So what goes up also comes down. But when they are emitting the frequency, they're emitting it in all directions, back in the direction it came from, as well as back outwards. So therefore, in the direction that you're looking at it, only some of the frequencies, only some of the intensity of the photons will be coming towards you compared to the original or the rest of the continuous spectra. There's a continuous spectra which will appear brighter than the dark lines where they've absorbed it and then re-emitted it in all directions. Okay, I hope that makes sense. I'm not sure if absorption spectra are specifically covered in year 12 or not. If not, I think they should be. Yeah, because in Unit 5 in IAL, we don't really think about them. We just need to know how to use them for redshift, Doppler shift, for example. Okay, part B, it goes to say about the diagram shows energy levels in a hydrogen atom. Yeah, just like I showed you with the numbers on the page, the lowest energy form to the highest. Yeah, and they're given in electron volts because joules is a large energy. It's not to scale. Okay. The absorption spectrum for hydrogen includes a set of lines that all derive from transitions, changes in energy levels, involving the n=2 level. Okay? One of these lines is known as the hydrogen alpha line. So it corresponds to the n=2 level, or transitions involving n=2. Deduce the transition involved, yeah, which is responsible for the hydrogen alpha line. So can we work it out? The wavelength of the hydrogen alpha line is given as 656.46 nanometers. So they're giving us the wavelength, and we got to change that into electron volts, and then look at which transitions involving N2 will correspond to that. So it's a multi-part problem. So once you know the wavelength, you can work out the frequency, which then allows you to work out the energy in joules. Once you know the energy in joules, you divide the energy in joules by the electron charge, and it converts it to electron volts. Okay? Then you look at the difference in the energy, yeah, and you can work out which ones will be the energy that you got linked to the n=2 level. So I haven't done it, and we'll look at the mark scheme because they will have done it for us. Oh, this was the 6-mark question from before, the content that they were looking for. Yeah, I'm sure I covered it all. Electron discrete energy levels, yes, I got that mark. Absorption of a single photon causes an electron to move to a higher energy level. I'm not sure if I wrote it or spoke it, so if I didn't write it, I might lose a mark, but I did mention it. Photon energy equal to HF, yeah, so it's proportional to frequency. I think I've got that. Energy absorbed photon must equal the difference in energy levels. I mentioned that. I put it down as delta E, so I've got that one. And the changes in the energy levels are specific to each element. I said each element is unique because of the energy levels, and a different wavelength or frequency are light or absorbed. I'm pretty sure I got that one too. Okay, now how well I write it out will determine whether they give me 6 marks, not just putting the ticks here. Okay, so to get the part B, the calculation, you get the frequency from the wavelength. Remember, nano means 10 to the minus 9. So you get the frequency is 10 to the 14 hertz. Okay, then you change it into joules. Yeah, H times F. H is 6.63, that's Planck's constant. That's given to you in a data sheet. So that's Planck's constant there. Okay, so we got it in joules, and then divide by 1.6 times 10 to the minus 19 gives you the energy difference, the energy transition of 1.89 electron volts. So one of them, then it has to be linked to level 2, 1.89. So we want to look for a 1.89 electron volt transition involving here. So this plus 1.89 volts, yeah, will give you, I think, 1.51. So 1.512 there, is that 1.89? Yes, it is. So this transition from here to here, the delta E is equal to 1.89 electron volts. And that is what you would work out would be the transition there. Okay? So you would say it's the transition, the absorption line will be pushing an electron up from n equal 2 to n equal 3 will be this line. So this line will bump it up from 3.4 n equal 2 level to n equal 3 level. Okay, hope that makes sense. 6 marker and 18B, and here comes 18C. It says in 1868, Huggins analyzed light from a star called Sirius A. The wavelength of the same hydrogen alpha line for the light from Sirius was slightly different from what we'd been told from the hydrogen alpha line observed in from a source in a laboratory on Earth. Okay, that's because of the Doppler shift. Sirius A is moving relative to us. So Huggins suggested that this difference could be explained by the Doppler shift. Yes. And could be used to determine the speed and direction of the star's relative motion. Okay. Relative to Earth. Okay. So assess his suggestion. Yeah. So you've got to say that, well, if it's red shift or blue shift, if it's shifted towards the red end, it's moving away from us. If it's shifted towards the blue end, in other words, the difference in the frequency is in one direction, it'll be blue shifted, therefore moving towards us. And the amount of the shift corresponds to the velocity. Yeah, so therefore he'll be correct. Okay, when you work it out. We'll have a look at the mark scheme right now. Part C. There it is. It says, according to the Doppler shift, if the source is moving away, the wavelength will increase. According to the Doppler shift, there is a change in wavelength which is proportional to the velocity. Okay, that's part of Hubble's law. So you can write, yes, he's correct, because the speed and direction can be determined. Okay. You can do it the other way around. Converse statement, it'll be allowed if you word it the other way around. Okay? And once you work out the shift in the wavelength, it allows you to work out the recession velocity. Okay, so that was 18C part 1, going back to 18C part 2. Okay? Sirius A has a component of velocity away from the Earth with a known velocity of 5.5 kilometers per second. The wavelength of the hydrogen line observed from a source in the laboratory, so the original one, is 656.46, so that's the original one, so I put an O there. Calculate the wavelength of the hydrogen line as seen in the spectrum of Sirius A. Okay? So it's moving away from us, so it's redshifting, so it should be getting longer. So the delta L you can work out from this will be equal to lambda naught, which we've been given here. And we know V, and of course C is known. So we know lambda naught, we know V, and we know C, and we can work out the shift. It should be red shifted, so it should be getting longer. So lambda dash delta lambda must be added to lambda naught because it's getting longer. So you add the 0.012 and you work out that the wavelength that you put in here will be 656.47. Yes, if you want to put one extra digit, one more significant figures, the next digit is 2. And don't forget the units. I've forgotten the units. It will be meters. Oh no, it will be nanometers. Nanometers. Okay? So I nearly lost the mark because of the units. Don't forget units. Okay, that's another 15-mark question done. Question 19. Is that the last one? Yes, so we have to finish the video. I apologize for such a long video. 2 parts, not bad though, especially on a Monday night. Nuclear decay is described as being spontaneous and random. Okay, so nuclear decay is the year 13 topic, so in IAL it will be in unit 5. State was meant by spontaneous and random in this context. I think it's quite a difficult question because in English they mean something similar. So spontaneous means we don't know the cause. Yeah? Appears to be independent of external conditions. Very difficult, I think. But once you've done it once, you need to make sure you've got notes on this. Random means you cannot predict when a decay will occur or which nucleus will decay next. Okay? So that's what random means. So any of the nuclei can decay at any time, and you can't predict which one, but statistically you know the number that will decay in a certain time on average. Explain why the decay constant of an isotope can be determined even though, what we just said, the nuclear decay is random. Well, it's because there's a statistical probability which is quite accurate when you deal with very large numbers. That's the kind of language you've got to put in for the 2 marks. You can have a look at the mark scheme later on and see if your wording is good enough. Okay, part B says radioactive source used in a laboratory emits alpha and beta radiation. Okay, describe how the percentage of activity due to beta may be determined using the infamous Geiger-Müller tube and rate meter. Okay, so the Geiger-Müller tube is a detector, but you need to count it, so you attach it to a counter, which is a rate meter. So first of all, you need to measure the background radiation without any source. Yes, always you need to do that. It's like your 0 error. Measure the count rate with the source. So without, then with the source. Correct for the background. That means you remove the value that was there and you do it a few times and average it. So you know your average rate of background count with your Geiger-Müller tube sensitivity and the rate meter. And then you absorb the alpha with paper. Then you measure the count rate again with the alpha removed. Again, you correct for the background. And then you calculate the percentage of the count rate which is due to alpha. Yeah? But I should have done it for beta, so the rest of it will be beta. Okay? So I'm not sure if I'm going to get all the marks. Let's have a look. Part B. Part B. Okay. Use paper to absorb the alpha. So yes, I'll get that. Measure background. Yes, I'll get that. And measure the count rate again. They haven't said correct for background. So I've got extra. And then the percentage will be with the paper minus the back. Oh, here they've done it's correct for background. And then from the source minus the background, we'll get the 1 mark. Okay. I'm just questioning whether that percentage is mathematically correct for the beta, but it's rather late at night. It's 9 p.m. and I've been working since 6:30 this morning. So you'll have to check it for me if you want to leave a comment in the under the YouTube video. I will try and have a look when I'm more awake. So we've got 19C to do, part 1 and part 2, and then we're done. Looks like it's half-life, activity, and something I can't work out without reading the question at this time at night. Okay, so 19C1. The Americium, I call it, I think it's pronounced Americium, is used, a man-made isotope, used in schools as a source of alpha radiation. Used to have it in my last school. Over here we don't have any sources where I'm working currently. Yeah, it was bought 34 years ago by a school. Okay, I remember this question now. Determine the percentage of the initial activity that will be expected today after 34 years. Yeah, well, the half-life is 432 years. So is 34 years going to make much of a difference? Okay, so the half-life is T half. Now to work it out, you need to use the natural logarithmic equation for the decay. Activity equals initial activity times e to the minus lambda t, where lambda can be worked out from the half-life, and you can leave it in years. So natural log of 2 divided by 432 gives you this value per year. Okay, so if you multiply this by 34 years, I've just changed the equation to put the fraction a over a naught on the left. It'll just make it easier. And if you put the number in, you'll see that it'll be 95%. Yeah, 0.947%. Okay, so the percentage of the original activity will be about 95% still remaining, as I told you. Okay, so basically you just need to know how to use the E function on your calculator to get the answer. Okay, so that's why here is a fraction, and I've just multiplied by 100, and that's why I put a and a naught on the same side of the equation. Okay, you can have a look at the marks and see how they give the marks. Do that later. Final part of this exam, the decay products of Americium are unstable and undergo a series of further decays. Okay, I prefer calling Americium than Americium. The table shows the first 3 decays in this sequence. Okay, first decay product is Neptunium. Yeah, so Americium into Neptunium by alpha. So it goes this way. So you can even do balanced equation. Half-life is 432 years. Then the Neptunium decays into protactinium, 233, again by alpha. And that's got a 2.1 million year half-life. So it's going to decay very slowly. And protactinium decays quite fast into uranium. And it's by beta. And it's got a half-life in days. So the protactinium won't be a large percentage. Student states protactinium emits beta when it decays. So by now, the Americium bought 34 years ago will be emitting a significant amount of beta radiation. Is that true? Well, let's have a look. The Neptunium has a very long life. Yeah? So by the time, in 34 years, not much of it will have decayed. It's a very long half-life, 2.1 million years. So in 34 years, and it only emits alpha, along with the Americium before it. So far only alpha. So very small amounts of protactinium will be present, yeah, after 34 years. Do you agree with that? So I'm saying the student is wrong, yeah, because he said it would be a significant amount of beta radiation. Student is wrong. It is not a significant, it would be insignificant. And there, finally, we have done a full run-through of the 2024 paper from last summer, and we've done 90 marks. I hope you found it useful. Don't forget to show your appreciation, like the video, share it with your friends in other countries, other schools who are doing Edexcel Linear, and it's very useful for students who are revising for IAL Unit 5, especially if you're retaking Unit 2. Be perfect for you. Okay, so this is the last bit. We got the 95% here for using the activity equation. Yeah, and this is a very common equation. You need to know how to use that. And here's the final bit, which we just went through. I'll let you stop the video, pause it when you want, and thanks for watching. Make sure you subscribe so you know when future videos are made. Bye for now.